Okay, yeah. Hi everyone. So yeah, my name is René, and I'm a PhD student at ISTerre, and I work with Leonard Seydoux and Michel Campillo. And well, as a title, I kind of put a very general title, which is also the title, let's say, of my thesis, which is exploring seismic time series with artificial intelligence. And during my first year, I tried many different things. And in the end, what we found is that the concept of blind source separation is quite interesting to find different types of signals in the seismic time series. So blind source separation is basically what we do a lot. For example, when you're in a bar and you try to focus on a certain voice and muting all the other voices. And so this concept, I would say, is quite interesting for seismic or applications in seismology. And a very interesting data set for that is actually a data set which was recorded in Hamburg when I was still a master's student with Celine. So we installed 3 broadband seismometers close to the city of Hamburg, and around you have lots of different types of noise sources. So you have a highway going this way, there's a train or railway going that way. The city of Hamburg is located over here, and then there's also a gravel pit with trucks working on it over here. And then also inside the soil and in the air, we have like different environmental sensors to check for certain types of medium changes, like if the temperature, for example, is changing or the water content. So all that makes it a very interesting study case for blind source separation because we have different types of sources, but we also have potential medium changes which we can observe. And then so we took a certain time period where we had an interesting medium change. So you see time series from January to April 2018, so 4 months of data. And in red you see the curve, the temperature curve measured above the ground. And we can see that in February we have nights with freezing air temperature, and we also have days with freezing air temperature. And in blue we see the temperature curve at 5 centimeter depth, and we can see that the ground freezes not, or the ground frost doesn't penetrate deeper than 5 centimeter depth. So this means we have a really, really thin surface layer with a high velocity. And we can also see this in the dV over V curve, which we measured from the noise cross correlation of the 3 stations. And what you basically see is we have a velocity increase due to the freezing, then a decrease due to the thawing, and then again an increase and decrease. So note that the axis is flipped. So that's the medium change, which is kind of continuously happening during the time period. And then the idea was, okay, can we detect this kind of medium change directly from the seismic time series without doing cross correlation, spectral whitening, stacking, and so on. And so that's the original data. You can see again, it's the same time period from January to April 2018. And here you see frequency range from 0.1 to almost 100 hertz, which is the sampling frequency. And what you see in the original data, so it's the east component, are these fringes due to day and night and due to week and weekend. So it's kind of the urban imprint in the seismic data. And then I will not go into the details of the algorithm we use because this is then on the poster, and also it's a bit too much. But basically what this, let's say, machinery is doing is to look for patterns in the data. And what we found is it blindly detects the freezing and thawing pattern directly from continuous seismograms. And so yeah, one main part in this machinery is the blind source separation. And so we can find, as I said, like one, we call it feature, which tracks the freezing and thawing cycle from the data. So it looks really like the dV over V curve we saw before. And then we can use that kind of feature to go back to our original data and filter it. And then what we see is that we remove completely the urban imprint, and we can highlight, well, it's not really visible here, but we can highlight the freezing patterns. So I hope you believe me. There's a kind of decrease in amplitude in the high frequency domain above 10 Hertz. And now still this could be related to any kind of source signal, but when we model the H over V response due to a thin layer of ground force, we can actually confirm that this is how the data would change due to the freezing. And yeah, from there on, I think the interesting question is like, what other patterns can we detect blindly in seismic data, and how can we extend the concept of blind source separation to seismic arrays? Because then we have much more information about different types of seismic sources. Thank you.